industry and the academic side. So there will be neutron coatings. We have tested indium oxide glass, which silicon oxide again is part of it. A new crystal one of the professors have created, and an adhesive failure testing parameter. So neutron shielding material which using lithium basically obstructs the gamma. So I'm not completely much familiar about this. If any questions, I will forward to one of the postdocs students. So the whole idea is they are trying to use a lithium to basically get, how do you put it?
So we have to use enriched lithium in a polymer material to shield the low energy neutron in neutron beam experiments. So it's mostly like for academic use at neutron beam facilities. But basically, if a high energy neutron hits lithium-6, it does not emit gamma rays like most material does. So it basically shields it and makes it less dangerous. And there's less background noise and imaging and stuff like that.
So this also has a similar application for, let's say, if you want to have space suits and reduce the gamma radiation which affects human body. So that has a future application as well that can be further developed. But currently they are just using for detectors to reduce the noise level. So this sample was a little bit difficult to work with because of the lithium aspect of it. So we definitely had initial test parameters of a lithium fluoride that has been provided. So these are basically two different graphs, one with an enriched lithium and coating system, and another graph is basically a standard lithium fluoride and coating system. So the blue graph on the right basically shows the lithium powder as an initial reference that we have used, and your fluorine component that basically pops up. Now the lithium, we didn't find anything on the top surface. So we definitely need to do a lot more work to actually find out the lithium where it's visible right now. The coating is on top, no lithium, but we need to do a depth profile to actually find out where that lithium level is. Because lithium is very reactive, so that's where we have to be a little bit slow and not damage the coating system and still get a lithium signal. So right now, this is all we have got up till now, that we are getting the fluorine component that is part of the polymer system. That's only we have detected. We have not detected the lithium on the top surface. So how that actually trails back to their applications, I'm not much familiar with it. So I'll have asked your questions specifically for that to the postdoc, Abigail. Okay. All right. Now the next one is cohesive failure for bond primer. So you have basically a primer and you have strontium chromate coating on the metal, which basically completely pulled off. So we basically test on this side. That's what the data on the left-hand side we are seeing. And basically the metal, which completely, there was complete failure. So that data is on the right-hand side. So on the left-hand side, we definitely, again, identified organic silicon, which is at 102 binding energy, and strontium in there. We didn't find much chromate in here to basically get a good identification, but there was some presence of strontium chromate in this area. On the metal side, we basically again detected strontium pretty strong signals. There was a small presence of organic silicon again, and some part of the chrome signal was present as well. The signal to noise ratio was low because the chrome level was quite less. So, yeah.
We are sure definitely organic silicon.
Okay.
Or because the metal itself is 2024, and I think that's 2024, it has also silicon inside. I asked the president, are we sure that it's organic silicon?
So the organic silicon signal basically at 102. If you have a silicon metal, that will be in. Yeah, so it will be, see out here, we are seeing slight elevation. So that would be your silicon metal. Tim, what is the silicon metal peak energy again, binding energy? Okay. So probably that is why we are seeing a slight hump in here that might be the silicon metal itself. But this particular peak is definitely a silicon, organic silicon. See out here, if you compare this silicon, we are not seeing any kind of elevation in here. So no silicon metal. But in here, there is a slight bump in there. So this could be identified as silicon metal. But this particular larger bump is organic silicon. Okay. Okay. Now another interesting test we did was hydrophobic coating or ceramic coating. Now a lot of people are in industry like, oh, we got a ceramic coating and it's a very good coating where we don't have any dust stick to it or the water doesn't stick to it and it protects pretty well. Yes, but how long does it last? That's one of the biggest questions that everybody is asking. And that's why aircraft industry is very cautious of putting on the aircraft, because if they put it on an aircraft, will it last for, let's say, 300 flight hours? And because if they put this material and if it just goes on the first flight itself, they cannot put a de-icing fluid on the aircraft. So we did basically a Tabor test, and we did a lot of testing in the past. The problem of hydrophobic coating and ceramic coatings are very thin. That's why when we got the XPS, that was a very revealing data of, okay, if we do a test, how much of the coating is still left. We can do a contact angle and basically find out the surface free energy and the contact angle and see the ratios on that. But the coating itself, how long it's last. So this is an example where we basically identified this, that was a silicon-based coating, and this is your Tabor wear resistance, your standard Tabor wear where you basically run through a cycle and see how that coating lasts. So that gave us a very good detail of how many cycles comparatively it lasted. So that is more revealing of rather than an answer of, okay, if we have that coating, some of them say, okay, even if it wears out, we still have the coating in there that will still protect or give hydrophobicity. But if you don't have a silicon or a fluorine component, that is one of the main ingredient, and it's just on the top layer, and once the first cycle is gone through, it's sometimes completely worn out. Some of them might last longer. It depends how your chemistry is built up. So this was one of the examples, and this is the data that shows that it has completely worn out and you're basically getting your coating system more. Okay, next sample is an indium tin oxide coating on a glass. So the two applications that I'm familiar with is dye-sensitized solar cells. For my master's, I basically used for solar cells that application, and that is one of the conductive coating. The another application is for windows on an aircraft for conductive coating. So when an aircraft has a static buildup, it basically, because of the conduction, it basically dissipates. So we were looking at the ratio of indium and tin, and we've all got different percentages of what those percentages for different windshield there are in the industry. And your silicon, again, this one is silicon dioxide. So you see at 102, that is your basically organic silicon, which is, this one is more on the left-hand side, which is defined as silicon dioxide. So that is definitely a clear difference between a silicon dioxide and a organic silicon. Yes.
Actually, the actual coating is on the glass.
Yes,
So then, where is the glass silicon?
that's the glass material. One of the silicon is the glass. So the next,
The silicon is not the organic silicon.
no, this is not organic silicon.
So then it's organic silicon. Why is it four?
It's on our 103, that's your silicon dioxide.
Then I think that we cannot give you data that it's silicon. It's 104. It's organic. But this is
Organic is 102 binding energy, and silicon dioxide 103, 100, around 103. Okay.
so then it's not organic.
No, this is not organic. So the next aspect, the whole idea was to identify silicon dioxide as basically do a depth profile and see how the coatings and how it's basically affected. So in this, your indium has the highest percentage, and as we go along in the etched profile, we basically has reduced after a very long etch process. And then the tin, which is the blue, is consistent throughout and slowly degrades over time, but the percentage is somewhere in the around less than 10%. Now the silicon dioxide, which is almost zero, it basically start picking up. So this is the region where your coating system is starting degrading and you're showing up the windshield material itself. So this is an example of your conductive coating and how it will affect the surface. So we still have indium overall, it stays, but your tin is basically dropping. So that's where your silicon is basically showing. Again, your material is, the data that we are getting is a depth of 10 nanometer. So it doesn't mean that your silicon and is completely exposed. It just gives you a parameter that, okay, at this particular point, I'm now starting detecting the silicon dioxide, that is a windshield of the aircraft. And we are basically started detecting, and when you start seeing a huge drop, that is the point where your coating is basically degraded. Now, Thermo Fisher guys have a lot of data with scaling at nanometer. Now, we don't have a baseline material where we can do a depth profile and do a standard. So that's why this one is basically an etch in seconds. That's what how we basically do the parameters. For how many seconds it is etched, and we do a test every 30 seconds or 60 seconds, whatever the parameters we select. And we collect the data again and basically go on again for the etch process. So any questions on this aspect?
Because that is so important. Can you go to the previous slide? That is the decay from the glass.
Yeah.
Can you go to the previous better and why you show that? That the previous the better exposed when you found the yeah. It's also 102, 103 same area how we can this is the previous one is the silicate again. What's the difference? How we can explain? It's the same area. I don't think any change.
Yeah, this one I'll have to check the data again. But this one is a definite indication that this one is silicon, organic silicon.
Previous one is the one. Same thing is the silicate. Now this is the silicone. Really we can separate the silicone and the silicone.
Yes.
Because it's the same binding energy you have.
This one I've just basically identified as a silicon material. I have not completely confirmed this, yeah.
And the position is
Yes.
right.
So your 102, basically this particular point is your organic silicon, and the later part is basically an silicon dioxide. Again, this data is a little bit noisy, so we need to get a bit better data set before I can make any comments on that. But this data is pretty well defined. So this one is basically 102, and this one is on this material.
Right, but maybe positioning and okay, finding energy, I think we are normally rely on the aspect here. So that is, I think, 102 over there.
Yes.
That I think we decide that is silicon,
Mm-hmm.
it's organic. Can you go to the glass hydrophobic? I think this is also very similar.
This is around 103.
Is that the decimal changes? One of them is a silicate, the other is a silicon. Is that right? Or previously said that 90 something.
90 something is elemental silicon.
Elemental silicon. Yes.
No.
And it
No,
maybe
not silicon oxide, silicon, pure silicon. Well, there's a rate, and it depends. For silicates, it depends. A metal silicate, it depends on the metal as well, because there's an interaction between the metal, the silicon, and the oxygen. And so the peak range there can be between about 101 and 103.
Okay.
because in the aerospace industry, it's one of the biggest ones.
Yeah,
It uses a lot of silicate, so it's really actually.
yeah, the thing is that you're not looking at, so at the moment, for space on the slide, we're showing one spectrum, whereas you're never analysing one spectrum in isolation, you're analysing the components to determine what the actual compound is.
So the software actually can pinpoint silicon or non-silicon.
You can differentiate by the peak, as long as you have the information in the other regions,
Yeah.
you can correlate that analysis. So if we're saying that the silicate is present, we need to have parts of the spectrum to
Okay, we have to combine that.
exactly, yeah.
Yeah, this is basically an example of an organic silicate. It's 102, and 103.5 is for silicon dioxide. Yes. But we need to basically identify the other aspects of the silicon as well. So out here, it basically gives it two different peaks for siloxane. So it's not always straightforward. We have to figure things out, and we have to check for other elements as well, because sometimes some elements are overlapping. So we have to basically, that test was only for just one particular area and not for the whole thing. So we need to redo an analysis more deeper and longer scans to get to good results. Okay. Great, thanks. Okay, I think so I'll complete the whole section.
Yeah.
Okay. Okay, so one of the other professors has created a different type of crystal. It's a tantalum based. So we have basically identified the tantalum, and we need to definitely have a more further analysis because it's not a standard tantalum 5 that we normally see. It's a lower oxidative state. So that's where the professors are going to provide another samples for us to basically analyze. And basically finding that we have phosphorus as well. We have selenium data. I don't believe I've shown that one. Okay, that's not in here right now. But that is basically for one of the crystals, one of the professors is trying to publish a work on this. So we're not sharing a lot of information, but just limited to this at this point. The other aspect, one of the other crystals that we created, the way he mentioned is the K2 ion, germanium and sulfur combination is basically used for thin coating on top of a glass material and basically can reduce the laser energy levels. So in there, we definitely basically identifying the potassium states and different carbon states and sulfur. So this requires some more better analysis because the powder form, sometimes what we have received, has some of other oxidative states or contamination. So this also again is an initial work what we did for one of the professors in the WSU. Okay, so I don't think so I have any other slides at this point. Any questions on what I've got? Okay, so we can break off for lunch from 12 to 1, and after 1 o'clock, then we can reconvene again, and Dr. Tim Nani can go on with his side for the coatings. Okay. Thank you.